So my current research is focused on the SpiNNaker project. SpiNNaker is a crude contraction of spiking neural network architecture, where the goal is to build a machine incorporating 1 million ARM processor cores, which we can use for real-time brain modelling applications. Now, with 1 million cores, we only get to about 1% of the scale of the human brain, or as I prefer to think of it, 10 whole mouse brains, which gives you some idea of the scale of the problem that we're taking on here. The physical machine occupies, or will occupy, 10 19-inch racks. So these are standard data center cases, about 6 or 7 feet tall, a bit over 19 inches wide and about 1 meter deep. The machine will be built here in Manchester and will be based in Manchester. At this stage we have one of those racks populated, so 100,000 cores, which is about 1 mouse brain's worth in terms of network complexity. Of course, modelling a real mouse brain requires lots of biological detail that we won't be going into, and knowledge of the network that doesn't currently exist, but it just gives you a feel of the scale of network that we can model on the machine. The physical design of SpiNNaker is really reasonably conventional. We have the chips, each of which has 18 cores on. We mount 48 of those chips on a circuit board, which is about the size of an A4 sheet of paper. So that gives you the order of 1,000 processors on a circuit board. And then we stack the circuit boards in card frames, so they're plugged into standard racks, quite close together, which we can do because we've been very careful to keep the power consumption under control, so there are no real hot spots on the board, and therefore it's quite easy to air cool even when they're spaced quite closely together. So we can get 24 boards across the width of a 19-inch card frame, and we can stack those 5 frames high in a 19-inch rack, including allowing space for cooling and so on. And that gives you 120 boards, each with 864 processors, which is 100,000, over 100,000 processors in a 19-inch rack. So the PCBs look pretty conventional. They're just lots of little black plastic packages soldered together in a slightly unusually regular array. The thing you'd notice about the board is it is highly regular. I can show you one if you want to.
Would love to see one, yeah. Is there one here? Have you got one?
Yeah,
here?
yeah. Can we shall I? Yep. So this is one of the SpiNNaker boards. This one's packaged in its own acrylic box. You can see the SpiNNaker chips. The name gives us an obvious logo of a SpiNNaker sail, which is quite attractive and easy to put on the chip. So you can see there are 48 chips on this board. It may look like they're arranged in a square, but actually topologically they're in a hexagon. So the board is a hexagonal subsurface of a toroid. The boards have high-speed connectors on the edges, and that allows us to connect multiple boards together to build the larger systems. So when we put 100,000 cores in a rack, all the boards in that rack are arranged on a single continuous toroid, which keeps the communication efficient. So this is a 19-inch card frame with 24 SpiNNaker boards in, 20,000 ARM processors, and you can see the boards are all linked together through high-speed links, which puts the chips into a continuous single toroidal surface, and then the boards are connected through a network switch to an Ethernet system, which is used for loading software onto the machine. On the top of the box there's a robot with a single SpiNNaker card on its back. The robot is built by Jörg Konrad at the Technical University of Munich, and it has a couple of vision sensors from Toby Delbruck at the University of Zurich on the front, and that can be used to build simple neural robot controllers that run on the SpiNNaker board.
So that's a single card that's basically controlling the robot?
Well, it's 864 processors, which is more than a robot will usually get. Where are we going now? I'll show you the big machine. That's yeah. So we're walking through the IT building here, and so this is a 100,000 processor SpiNNaker machine. It has 5 of the card frames that we saw in the previous shot, and now you can see the wiring that wires them together. It's got a lot more complicated and stringy.
It's going to be one of the primary problems, is it? All the wiring?
Yes, it's quite complicated to wire. It took a PhD student 4 hours to wire the machine up from the front. The machine is basically connected to the Ethernet, so you can control it remotely. You need some kind of host machine to compile the network on, and you download it over the Ethernet onto the SpiNNaker machine itself, and then the thing then runs and the network evolves in real time. Even the small card frame's a bit noisy. We were very careful about the power consumption, but we're still packing it together sufficiently densely that it needs a bit of a draft to keep it cool. Apart from the communications network, the Spinnaker architecture looks reasonably conventional. It's a massively parallel computer. Each node is an ARM processor with a certain amount of code memory and a certain amount of data memory. And so programming the processor cores themselves is reasonably conventional. Because we're aiming for real time, we use what's called an event-driven programming model. So instead of having a single program that runs and loops around, the programmer writes a number of event handlers, which are little bits of code that get invoked when particular events happen, such as an incoming packet arrives from another neuron. That calls a little bit of code which says, well, what do I do when this input spikes? And what I do is I look up the synapses that are connected to that input, and I pass the relevant level of signal through to the neurons that are modelled here, and that may or may not cause some of those neurons to spike, and if they do, then I drop more packets into the fabric and so on. The design objective of SpiNNaker was to model about 1,000 neurons in real time on each ARM core. So with a 1,000,000 core machine we get to 1 billion neurons in total. Now, at the moment, we're still tweaking the efficiency of the software, and the current software implementation maps about 256 neurons to each core. So we aren't at the efficiency we're ultimately aiming for, but we're close. The basis of human memory is not really well understood. I mean, computer memory is relatively very simple. We arrange a silicon structure, and we have a cell where we can store a 0 or a 1, and we know exactly where that information is, and if the cell breaks, we lose that information. Human memory doesn't seem to be like that. Human memory seems to be much more distributed. We all, through adult life, lose about a neuron a second, and so if any neuron was critical to a memory, then each neuron we lost would be some memory going. And that doesn't seem to be the case. It seems to be that biology has found ways to store information in distributed ways, so if you lose small components, you don't lose the memory. The aim of building the SpiNNaker machine was to contribute to the scientific grand challenge of understanding how the brain works. We each have this thing inside our heads that is clearly vital to the way we perform our daily tasks, but we don't know how it works fundamentally as an information processor. We don't have deep knowledge. We know lots about the fine detail about the neurons and the cellular biology, and we know quite a lot about how activity moves around inside the head. But the interesting stuff for me as a computer scientist is how information is processed, and that's at levels that we can't access either from the bottom up or from the top down. So really the only instruments we have for increasing our understanding are computer models. Now, of course, the computer models have to be informed by what we do know about neuroscience. So this work is very much a collaboration between disciplines, neuroscience, computer science, psychology, all come into play, with quite a lot of mathematics too.
Oh, it's a little bit similar to the yellow one, so we put it a bit closer to the yellow one. And then comes another data item, and this is obviously quite similar to the yellow one, so we put it closer to here. And then so over time we get all these data items.
Don't want to just dash something off, but I read it off and make sure that my sentences are well constructed and spelled correctly and so on. So it took a long time, and it turned out that I was spending, I would start out with an idea of what I was going to do that day, and then 4 hours later